All right. Good afternoon, everybody. Still have a voice, so we're okay for now. Today I wanted to talk about kind of some basics of growth equations. We did a lot of decay stuff in the first part of the semester, mass balances with typically zero or first order decay. I wanted to kind of revisit that a little bit to go over growth, specifically in the context of dealing with microbes. Microbes growing. We've been talking this section about how do we quantify microbiology and its role in the environment. And so growth equations apply to certainly that, but also a little more broadly to human populations, to, let's say, a growth of electrical demand, for example, or something like that. So as we're considering growth, we've got a few examples of human population growth, some things to take a look at, and then we'll transition from there to go into biological oxygen demand, because that's another thing I'm planning to give you the homework about, and I want to try to cover some of it before you go on break. Tuesday, I still am planning to go over the exam 2. So that's still my plan right now. And so I want to try to get in some of the BOD stuff this class so we can kind of wrap that up when we come back from break. Turns out there's not very many classes left. It's been a strange semester, to say the least. Okay, so any questions, issues, concerns before I begin? So, all right, so we'll go ahead in with growth. So a growth equation is very straightforward. If you're talking about exponential growth, it's going to be an exponential equation. Could look at the doubling time, and the corollary there would be half-life. I think we did talk a little bit about that, but something with radioactive decay, for example, would be you'd have some length of time in which you expect that substance to decay by 1/2. So the very same principle we can apply to exponential growth. How long does it take before the bacteria doubles in population? If we're talking about human population or something like that, often, in bacteria as well, at some point you have a limiting factor. For bacteria, maybe you're running out of nutrients and food. For human populations, maybe we can see this actually as countries develop. They tend to scale down their fertility, and that's has to do with education and essentially infrastructure and opportunities specifically for women in those countries to have control over birth, right? So birth control plays a vital role there, and education and resources provide a lot of that. So if we take a look at projections, and this is from an older book, I think published in 2008 or something, so slightly dated. If we take a look at projected human population, I think we'll take a closer look later, but you can kind of imagine if nothing ever constrained the growth, we would have something that looked like that. It would be exponential, and you'd have billions and billions and billions of people. Before long, you'd have trillions. But that's not reality. And so we'll talk a little more about that in a few slides. So just kind of that concept, we have half-life, we have doubling time. Here's a quick problem about population growth. So it took about 300 years for the world's population to increase from 500 million to 4 billion people. If we assume exponential growth at a constant rate over that period of time, what would that growth rate be? It's coming from an example where there's like some rule of thumb we could use as well, so just don't worry about that. So using a calculator. hopefully this should be a fairly straightforward issue here. We can recognize change in population over time, dn dt. That's going to be some presumably first order because it requires people to make more people, right? It's going to have some rate constant times n. And so if we do our integration, this is going to essentially be just like any other batch reactor mass balance kind of a deal, where we could say n over n naught is equal to e to the kt. The difference here being instead of a negative for a decay reaction, we have just positive there. You know, we could rewrite this as dn over n equals k dt and integrate that from n to n, from n naught to n, and that's where we're getting this value, right? And we'll just go 0 to time t. So then we can use this to put in those numbers that we had. We were given 300 years, went from 0.5 to 4 billion. And the nice thing about this, the fraction this way, is it doesn't really matter. The billion component of it will cancel, right? So we can actually just kind of ignore the billion part. So we'll take the natural log of both sides. That way we get rid of the e. So natural log of n over n naught equals k times t. And so we have natural log of 4.0 divided by 0.5 equals k times 300. So it asked for the rate. I think perhaps it was referring to the rate constant, and I think years are a reasonable time to give it. The units here for the time are years, so we can solve for that k in per year. That's going to give us, I guess in that sense, a rate per year, for like a percent per year type of deal. And then if we put this into a calculator, which I did not do, which I should do, and we'll see what we get. So let's take the natural log of 8, that's 4 divided by 1/2, divide that by 300. We can also take that and multiply it by 100% to put it in percentage. So k then is 0.693%. So that would be a percentage of the population growing every year, right? Does that make sense? Hopefully pretty straightforward. I suppose you could calculate the actual rate. So they say the growth rate, and if you're being really careful with the wording, I guess you could take the rate at the very start. You'd have to assume they're talking about the very start or maybe at the very end to get the total change in that year. That would technically be the rate, where the rate constant is what we solved for. I think they meant the rate constant, but let's not bother with that. So that would be then our answer, and that's per year. So the units technically, if we wrote it out as a fraction like we normally would, that would be 0.00693 year to the minus 1. Okay. All right. So let's do another quick one. We have a radon source, and there is some amount of it. Don't worry about the units there, 1.0 Ci. Just leave that as some sort of units of radon-222. So we have one amount of it, and the question is, what would be its activity? So this is a unit for the activity of the radioactivity of the material. I'm forgetting the actual term. But
does it matter with the calculation?
No, it shouldn't. Yeah. And it's saying that table 2.6 indicates the half-life for radon is 3.8 days. And okay, so all right. So for this question, we're given a half-life. So, you know, I provided this example. We could also give it a doubling time. So if we did like 3-hour doubling time for some bacteria, the same exact process would occur. And so I'm kind of showing this, even though this is decay, just to kind of refresh our mind and be thinking about these systems because we haven't touched mass balances in a little while. Okay, so in this case, we're given this radon has a half-life of 3.8 days. So we'll just say half-life, or maybe tau 1/2, we'll say, 3.8 days. That means that if we started with 1, we started with 2 and ended with 1, that's 1/2. That's our n over n naught, or our c over c naught. We can say that's, let's take the natural log of that, equal to minus k times t. And we know the t, so we can solve for the k. So we need to find this k and then apply it to the 5 days, right? So we know it'll take 3.5 days before that activity is halved. So how much activity will we have if we're at 5 days is kind of the question. So k then is going to be equal to the natural log of 0.5 times -1 divided by that 3.8 days. And so when we do that, don't really have a good spot for it. That should give us a K of 0.182 per day. Then we can apply that to the problem itself and say, well, what is our amount after 5 days? So if we were, let's call it C over C naught equals e to the minus kt. Well, in this case, we want to find C. We know the initial C naught is 1.0, so that's when we're calling back that, times e to the minus 0.182 days per days times 5 days. And you'll notice the units up here cancel as they should. And so then we can solve for C. Preferably without that in the way. Sorry. So we could say C is equal to 1 times, let's do 2.71 raised to the minus 1.82 times 5. And that'll give us 0.40 as our answer there. And this is in those CI units. Okay, hopefully we did that right. Looks good. All right, so done this already. Again, just kind of jogging our memory here, getting us back thinking about systems in these ways. And one thing to note here is we can potentially combine rates. We might get into this a little bit, probably after the break, in terms of what happens if we have some growth in one chamber and then some disinfection or some decay in the next chamber. Like, how do we model that going from one system to the next? Or perhaps even if we have competing reactions in the same system, how do we put that into a mass balance? We may take a bit of a look at that as well. Okay, but for now, just a few comments on population dynamics in general. If you're ever to take a look into kind of human population dynamics, there's a lot of interesting ways to look at it. You can look at a population that is growing, and again, this is data from our text, from not our textbook, from a different textbook that's a little dated. And so different countries, if they're growing, you can see a higher population for younger ages compared to older ages. Whereas more of a mature, sort of developed country situation, you have a kind of similar age groups around, and then maybe see some baby boomers or something, you know, having a larger fraction of the population. If we take a look at projected population growth globally, there's actually a neat website that I found. And okay, so this book, I think it was published in 2007 or 2008. And so this data is from sometime around 2005 when they made the predictions. Actually, it looks like the predictions are starting back here. So maybe the data is 2000 or even earlier. So this is population in billions. And one thing we can take a look at is if we are about here, we can kind of consider which model has kind of hit the mark, something around there, right? So depending on, okay, so that's our year. So that's the X mark that we're looking at. And then the question is, where are we right now in population-wise? Any of you happen to know what global population we believe we have?
7.9.
Hey Siri. Good answer.
7.846 billion.
Yep.
How do they estimate that?
It's a good question. This website should at least show some estimate. So this is a different estimate, right? Maybe that answer was from Wiki, and this one is somehow knowing when everybody dies and is born, right? And calculates it in real time, you know, updates. Certainly.
Wait, why are they
We're not just watching somebody just pass out, right?
Yeah, if you think of the implications of all this, it's like.
why are the payments amount to the best?
Just going up.
No, but like there's 250,000, there's 100,000.
It's this year versus today. Okay, so this is plotting. This is
Oh wait, that says birth.
claiming that there's 250,000 people that were born today, and about 100,000 people died today, so net growth there. A very good question on how do we know, and who's sitting there and entering all this data. Obviously they're not. Okay, so entertaining in some respects, but if we go through here, it kind of goes different populations. Another thing it does, I'm just gonna see if I can zoom my screen out a little bit. There we go. So if we take a look at the population or the historic population here, we do see an exponential growth, but for a long time it was not really very possible. Yeah, there we go. Okay, so this is dating back to year 300, for example, and then I think this is 1700, 1800, something like that, and then boom. I might add that off a little bit. Hard to read on my screen over there as well. At any rate, we can see that that's kind of what the population is doing, and in some regard, if we compare this to like microbes, it's as if we had a bunch of food and good resources and a good environment finally, then the population went kind of exploded. But you also see it's tapering off. Fortunately, that doesn't mean we're all starving and like killing each other to eat each other or whatever the bacteria might do. That it's different forms of population control, thankfully. You can also take a look at the growth rate. So we just did some calculations on the growth rate based on all that, and track that over the years. So we're looking back to 1950 and up to 2019, and we see that essentially the amount of growth we have does vary, but it is trending downwards globally in terms of the rate of increase, which would track, if we're to go back to our slides, that's kind of tracking with the fertility reductions we mentioned. So if we are somewhere near 8, right, if this is 6, we'd have a 7, 8, 9, something like that. Then we can track over here. And so far it looks like that slow fertility reductions, whatever that's referring to, is sort of tracking with it according to that plot. Who knows though, because models are never correct. Sometimes they're useful, right? So it might be the case that if we did a new estimate today, the divergences might be a bit different. I have heard some estimates that we're really probably not going to go over 10 billion people based on trajectories. So in some ways, that's good. I mean, human life is precious and a good thing. So assuming we can sustain it, then the more the merrier, I suppose. But on the other hand, it's good that people who, good to control it to the extent that we are, that individuals are interested in controlling their population. Okay, so they go through some more milestones. Okay, so this does say 2057 is their estimate currently for 10 billion people. But if you look at that growth, so that's 2 billion people over the next 36 years. I think we've been growing faster than that in the past. I mean, the data just showed us the growth rates have been decreasing, so obviously yes. But it's interesting. So take a look here if you're curious. Lots of data here. I think this is part of a bigger, I'm not sure. I think there's a site called World in Data or something like that. I'm not.
World in Meters.
Yeah. I'm not sure if this one has more content. There's some sites out there that are just amazing with how much content of data and data visualization that there is. So if you're ever curious, check it out. Okay, so that's just a couple comments on that. Now back to bacteria and oxygen demand. So, lots of people might be thinking, well, lots of oxygen consumption and lots of exhaling CO2. Well, microbes are quite a bit better at that in terms of how many there are. So when we think about oxygen demand, kind of already talked a little bit about it, but what we're really interested in is measuring an impact that wastewater has on the environment, or measuring kind of the quality, water quality generally. So oxygen demand is really important, because what we don't want to have happen is for our natural bodies of water to go anoxic, to essentially go through any sort of process that depletes them of oxygen, preventing the life in them from living. Now the lime green photo here is of a body of water going through what's called eutrophication. That's when you have too many nutrients, and then you get a lot of algae growing, and you might think to yourself, well, it's all green, that's algae, that's photosynthesis, right? You get lots of sunlight, they consume CO2 and produce oxygen, so you'll get more oxygen in the water, right? Well, there's a problem, because the population of algae then, first of all, will start to shade out anything below the first couple of feet. So anything below that is not getting light, and therefore any algae down there are no longer undergoing photosynthesis, because they can't. And in fact, algae, when they don't have light, will go back to doing normal respiration, like you and I are doing right now. We can't turn on the photosynthesis apparatus because we don't have one, but they have both. And so the bacteria and the algae that, so bacteria generally, unless it's a cyanobacteria, don't have any photosynthesis anyway. So any bacteria that are down there, any algae that's shielded from the sun, they're all now consuming oxygen and producing CO2. And given that the fact that there's a lot of nutrients there, obviously, they're going to be doing a lot of that. And when these cells that are happily growing and living up here on top die, they'll typically start sedimenting downwards, and their nutrients will be released and consumed by some other microorganism, further depleting the oxygen in the lower areas. So this is called eutrophication. There's a further problem that is also pretty obvious, and that is the sun doesn't always shine. And so at nighttime, you also have significant respiration, significant depletion of oxygen there. So eutrophication is generally a bad thing. Occasionally it might happen to a body of water naturally, but it's certainly not something we desire for our bodies of water. Okay, so talking quantifying oxygen demand and specifying what that is, we have to have a good understanding of substances that will lead to oxygen depletion. The first way to look at it would be the theoretical oxygen demand. The theoretical is talking about if we knew exactly what molecules there, maybe glucose as an example, then we could calculate exactly how much oxygen is required to metabolize that glucose. And essentially what we're talking about, that would be the maximum possible oxygen that substance could result in demanding oxygen, right? If we took it and heated it to burning, we would burn it and it would become carbon dioxide and water and maybe some other byproducts. Glucose, for example, would just be carbon dioxide and water. So let's do that. So let's calculate the theoretical oxygen demand for glucose. Let's take 108.75 milligrams per liter of glucose and calculate the theoretical oxygen demand. And that's going to be, by the way, in milligrams per liter of oxygen. Milligrams of O2 per liter. And keep in mind, we say oxygen, we really are referring to molecular oxygen O2 that we can breathe and that is available to these organisms. So you'll have to write out a chemical formula and balance it. for a simple hydrocarbon like that, that's got carbon and hydrogen and maybe some oxygens, you should be able to do that, and you should know that what we're doing is we're adding oxygen, creating carbon dioxide and water. had a chance? Okay. So I put up the atomic weights here for hydrogen, carbon, and oxygen. I balanced the equation here. We had one glucose, so that's going to be 6 carbons. Need to match that 6 carbons, so I put a 6 for the CO2. Then I thought, well, let's balance the hydrogens. We've got 12, and so that would be 6 waters. And then we'll take a look at the oxygens. So we've got 12 here, 6 more here, that's 18. If we divide that by 2, because we have two oxygens for every O2. Did I do it wrong?
Yeah, you have 24 oxygens on the left side.
Oops.
Yeah.
That should be 6, you're right. You're all looking at me like, he's wrong. Will he notice? Nope. Thank you. Okay, so if you balance it correctly there, then that's what it should look like, because I just forgot the 6 oxygens that I wrote in the glucose itself. All right, so there we go. And then, so that's kind of the starting place, so we know how many moles of oxygen are going to be required for every 1 mole of glucose that we are going to oxidize. And so, again, this is an oxidation process, and we're assuming this theoretical amount is the maximum extent of oxidation that we can theoretically achieve. So with that, we can take our 108.75 milligrams per liter of the glucose. We're going to find what the amount of moles we have of that and convert that into oxygen to see how many moles of oxygen we need to supply, and then convert that back to milligrams of oxygen. So the molecular weight for glucose, if we do that, should be 180 grams per mole, if I did that calculation correctly. And so that means we can take this 108.75, multiply this by 1 mole for every 180 grams of glucose, and we also have to account for the milligrams, so we need to do 1 gram per 1,000 milligrams. Okay, so that should give us some value here. I have in my spreadsheet. Part of the spreadsheet is wrong, so don't yell at me for having the wrong answer just yet. Oops. In fact, I'll go ahead and fix it. Okay, so if we take our 108.75 and divide it by 180 and divide it by 1,000, we should get 0.0006 moles per liter, or 6 point something times 10 to the minus, is that fourth? Yeah, fourth moles per liter. And I'm going to leave there's more decimal places I'm sure that we could look at. I'm just going to leave that in Excel for now. And we'll take that and then convert it back to, so that's moles per liter of glucose. And so then we can multiply this by, let's see, so moles of oxygen per liter then would be that 6 times 10 to the minus fourth moles glucose per liter multiplied by 6 moles of O2 per 1 mole glucose. I'm just going to abbreviate it GL. That's coming from our stoichiometric equation, of course, and that will give us a new answer. I'm also going to go ahead and multiply that by 1,000 milligrams per gram. And sorry, need 2 more things. We need to multiply it by our molecular weight of oxygen, which would be 32, which I also didn't put in the thing correctly, I think. So 32 grams of oxygen per mole of oxygen, and then multiply by 1,000 milligrams per gram. Okay, so let me just double check that I did get O2 and not make the mistake I warned you against. Yeah, totally did. Okay. Once we do that, that should come out to 0.0036 moles per liter of oxygen, or 116 milligrams per liter of oxygen. So look right. Cool. Okay, so that's a lot of oxygen. And if you remember back from, let's go and write this out. (116 milligrams per liter of O2). All right, so if you remember back to anything we did with Henry's law, stuff like that, it turns out that most waters at most can have 10 to 15 milligrams per liter of oxygen at saturation. So if we put in that much glucose and the bacteria are happy to go ham on it, to consume it, to undergo respiration, then you're going to end up with oxygen depletion and then some. They're going to be waiting for oxygen and going to be consuming that oxygen as soon as they get it, right? So they're going to be, they'll consume anything they have available to them in the water, and they'll look for more. So as maybe re-aeration happens, or as new water flows in and dilutes it, they'll still be consuming the oxygen. Okay, so that's sort of the theoretical amount. Turns out we don't normally know exactly what molecules are in our waste or in our water, so we can't normally calculate theoretically exactly how much is going to be consumed. And further, it's not usually completely mineralized like that in reality. So we actually have a couple other methods to provide us kind of better tools for understanding how much oxygen is going to be demanded practically. And one way is chemical oxygen demand. That's going to sound redundant because we were just like, hey, we just did chemistry. So how is this different? This is actually a chemical method. So it's a lab technique. You apply it, and you use chemical techniques to oxidize stuff, and essentially you track how much CO2 is produced as a measure of how much oxygen is being consumed. So if you track that CO2, you're going to have reactions like the one we just did, but there are going to be some compounds that maybe they don't combust all the way, and you have maybe more than just CO2 in your system. Maybe you have some other byproducts. So it's not going to get to the theoretical level. The COD, in that sense, is going to be, like, the value that you calculate is going to be less than the theoretical. But you can do this on a mixture of wastewater where you have no idea what kind of molecules are in there, right? You'd have no capability of predicting exactly what the stoichiometry is going to be. So this is kind of a little bit of a brute force method. It takes maybe a couple hours. I think I have a quick little video that may explain it for us with some illustrations.
Chemical oxygen demand, also known as COD, accounts for the amount of oxygen consumed in a solution by chemical reactions in order to consume organic contaminants present, typically measured in milligrams per liter. As oxygen is a fundamental element for degradation of any product, the amount of oxygen that is present and consumed in water bodies is very important. COD allows to estimate the effect of discharging polluted wastewater in the environment. When effluents with high COD levels are discharged in the environment, there will be a reaction of the dissolved oxygen, LO, available for the biome and biota in the environment. Consequently, the ecosystem will suffer losses in that area until LO is back to normal levels. COD can be tested by chemically oxidizing organic matter under conditions of heat and strong acids. Here, the presence of a very strong oxidant is necessary to ensure the proper measurement. Lately, the most common acid applied for the test is potassium dichromate, which is a hexavalent chromium salt and very strong oxidant, oxidizing between 95 to 100% of all organic matter. The technique involves a 2-hour digestion process in which samples are mixed with potassium dichromate, sulfuric acid, and metal salts. the last two added to suppress interference and catalyze the reaction. After the digestion process is finished, the oxidation is measured considering the electrons consumed for the reduction of Cr6+ to Cr3+, and analyzed by spectrophotometry. Since the potassium dichromate shifts from yellow to dull green as it oxidizes, the samples can be read in wavelengths of 600 and 420 nanometer. Another similar and complementary measurement is the biological oxygen demand, BOD. As the name suggests, BOD refers to the oxygen consumed in a solution by biological organisms, typically aerobic microorganisms, and accounts for the compounds that are not chemically degraded. Combined, these two represent basic measures that allow to estimate the final quality of the effluent to be discharged in the...
Okay, that seems a little awkward the way they've just phrased that, so I'm going to stop them there. I think the COD was pretty helpful. There's probably other ways you can measure the consumption of oxygen. In that case, they're looking at the oxidation state of that hexavalent chromium itself. You could potentially track the CO2. That's not an exact metric. We do use that for measuring total organic carbon. It's a similar process. And so that's kind of what I was referring to. Ultimately, the COD method is doing effectively that organic matter plus oxygen, catalyzing that, enhancing that, causing that, to get CO2, H2O, probably nitrogen gas, whatever else happens to be in here that can volatilize. Other stuff's going to be produced. But we don't necessarily get every last little bit of stuff to oxidize there. And the reason I stopped that video, because it made it sound like you're going to do that and then do your BOD. That's not the way we do it. And it's not really the case that something that is not degraded in the COD will be degraded by a biological system. Yes, there's some differences in what straight chemistry can do versus what biology can do, but actually the deal of it is, a moment ago I said that the theoretical is going to be greater than COD. Well, it turns out that COD is also going to be more than the BOD. And I guess maybe I could write that all backwards. Maybe it makes more sense. But BOD is going a smaller fraction than COD, which is a smaller fraction than the theoretical. So theoretical is like the total you could possibly have happen given chemistry. The chemical oxygen demand, then, the COD, is based on some method, how much you get. It's going to be a little less than theoretical because it's not everything's ideal. And then the biological is whatever's biodegradable. So you might see it biodegradable, biological, biochemical, whatever the case, it's biologically related oxygen demand. And so this is what directly relates to microbes, although as we'll learn, it typically takes about 5 days to get your results back. So it's a little slow. So you might see right from the get-go that if you could just do a back-of-the-hand calculation for the theoretical, that would be handy. Not very useful unless maybe it's just the glucose, right? Now, if you had the chemical method at hand, you could do this chemical digestion and get an answer in a couple hours. That would be kind of the next quickest one and would be pretty practical in some cases when you need a quick answer. Turns out you can track leachate from landfills in groundwater pretty well by measuring COD. If you want exactly what's happening in terms of the microbiological, the biodegradable portion of your waste, then you need to do these 5-day BOD tests. 5 days is standard, and I'll talk about that in a minute. Essentially, what we're measuring with these fancy little BOD jars is we have an oxygen probe inserted into the chamber, and we have some liquid in here. A lot of times it's like 300 milliliters. It's pretty standard. A limited headspace for air, and then we have this oxygen meter, and so we can detect how much oxygen is being removed over time. We always do this with dark bottles, so these amber jars, probably in a dark space. and we will typically incubate them to give them a little bit of temperature. The reason we have the dark bottles is so we don't have any photosynthesis that could occur, because it's going to be just a grab sample from wastewater or something. Maybe we dilute it. We can expect there's some algae or cyanobacteria in there that can do photosynthesis. We don't want that, because that's going to essentially contaminate our results. We also have a nice perfect seal there to prevent any exchange with the atmosphere, because then that's going to throw off all of our results as well. So that's kind of the strategy. There's a few particulars about how we measure it. And again, what we're measuring is the oxygen, and it's the oxygen that is being demanded because of the junk in the water. So we're using this whole metric as a measure of how much junk is in the water, how much bacteria food, biodegradable stuff. Okay, the same general principle applies. We're taking oxygen and eating those dissolved organics to form CO2 with respiration, but also some cells and some other byproducts that may not necessarily be a complete oxidation of the material. So this is one of the reasons why it's not going as far in terms of oxidation as the COD would. So a little more specifically, we would expect to form some CO2, some water, new cells, and what we would call stable byproducts, things like nitrate, nitrite, phosphate, some things like that are partially oxidized, they're stable, and they're going to be sort of byproducts of the digestion. Okay, I mentioned a few of these things in passing, but a few assumptions and principles. And by the way, we see this little 5 I inserted here. That means it's a 5-day test. That's kind of the standard. You technically can wait 4 days and measure it and use that as your metric, how much biodegrades in 4 days. And essentially what we're doing is we're looking at we're making sure we have enough growth of bacteria, and then we're keeping them there for long enough to watch the food be eliminated. And how much oxygen is removed during that time, it gives us that metric. So BOD 5 is just simply the standard, so you'll see it often just BOD, BOD 5. That's the standard. Okay, and what we do is we simply measure the before and after, the oxygen in that chamber. And by doing so, we can know how much oxygen has been consumed. Let's see. A lot of times we have to dilute. Earlier I was talking about we took a look at that glucose example, and we said we have like 116 milligrams O2 per liter demanded. Well, if our water in the bottle, and I think I may have misspoke, I think we don't typically allow headspace. You can see some in this one, but I think it's typical to actually avoid headspace so you don't have an extra pool of oxygen in there. What you're measuring is just the oxygen in the liquid. But that limits you to about 8 to 10 milligrams per liter of oxygen, because that's your saturation of water. So you'd aerate it and then put the cap on and measure. You'd have some amount of oxygen. And if you only have 8 milligrams per liter of oxygen in the first place in saturation, then you're never going to be able to tell how much for this sample, that 116, you're just going to measure 0. And that's not accurate, right? You're going to deplete all the oxygen, and your next measurement will just be 0. You went from 8 to 0. That doesn't mean you have 8 milligrams per liter of oxygen demand. It just means you ran out. So when we do these measurements, we actually have to take a few more precautions. A lot of times you have to dilute. And so in order to dilute the 116, if you were to dilute it by a factor of 10, you get down to 11.6. That's almost in range. So maybe you dilute it by a factor of 50. And so then let's say that's 11.6, and you divide that by 5 more. So that's down to around 4 to 5 range. And that should work, 5 to 6 range. So if you diluted it by a factor of 50, then you would have a sample where you could do it. This is a typical culture jar, but we'd never do that unless we covered it in foil, because we don't want any light coming in. Okay, so there is a subset of BOD that we would call nitrogenous BOD. So this is essentially related to the processing of nitrogen species. So ammonia going to nitrite, going to nitrate, and then ultimately denitrifying to N2. And if you track the oxidation state of the nitrogen there, you're essentially oxidizing each step of the way. It's very intuitive when you're adding literal oxygens to it, but I'm mentioning that because if you go, it's intuitive from here and then to here, but going to N2, well, there's no more oxygens on it, so it kind of looks like you've removed oxygen. I mean, you've removed oxygen, but it looks like you're maybe reducing it, but in fact, if you look at the oxidation state, it is another oxidation process. Okay, so anyway, the system here is that's requiring oxygen from the water, right? So you're depleting oxygen by doing these nitrogenous oxidations, we'll call them. We can think of those as something that would probably be in addition to the carbon, the straight up BOD, but a lot of times they'll be kind of mixed into the same, and we'll be observing them both at the same time doing our analysis. So you might see a problem asking you about different parts. You could do theoretical nitrogenous BOD if you had some specific reaction that you were going to perform, and you just need to balance an equation based on that reaction, right? So there's just wanted to make a note that that's a topic. Sometimes people will distinguish between the nitrogenous versus the carbonaceous BOD. Okay, so let's talk a little bit about how we calculate BOD, and this is going to be from those jar measurements. So we've got those jars. They are, we measure before and after. So the very simplest case is we have a jar, we measure before and after, and that's just it, right? So we could do the dissolved oxygen initial minus dissolved oxygen final. And if maybe it was river water and it had just a little bit of BOD in it, just naturally, then that would be all it is, right? But whenever we're dealing with wastewater, we're going to have to dilute. And if we're dealing with any water that's just rich with organic material, maybe you take a sample from a swamp and it's just kind of got lots of organics in it, likely you would need to dilute it. So you need this dilution factor where P is essentially the volume, and here we're calling it wastewater, the volume of your sample divided by the total volume in the jar. So I think I might have a drawing for this, but if we were to kind of draw a jar here, and it's filled with water, and let's say we've got 10% of it, we add the wastewater, and then we add some dilution water. And that should be pretty much clean water for the dilution, right? So that's what we're talking about, is we're filling this with some total, and the total is typically going to be 300 milliliters, but it's definitely equal to the volume of the wastewater plus the volume of the dilution, right? That's all this thing is saying. So the dilution factor, P, is what portion of the total is the sample. Okay. All right, and we're often going to be dealing with milliliters. Of course, that's 1,000th of a liter. So if we took a 1 liter bottle, cut that into thirds, that'll give you approximately the size of one of these jars. Okay, so with that, you really know enough to solve a problem. So let's go ahead and do one here. So a 10 milliliter sample of sewage mixed with enough water to fill a 300 milliliter bottle has an initial dissolved oxygen of 9.0 milligrams per liter. To help assure an accurate test, it is desirable to have at least 2 milligrams per liter of a drop in DO. So you have to have at least that amount of change for the for you to be able to trust the DO probe during the 5-day run. And the final DO should be at least 2 milligrams per liter. So you kind of have a window there. It should drop at least 2, and it can't have dropped all the way down below 2. So if you started at 9, then you have to do at least 2, and you could not do, more than 9 minus 7, essentially, is kind of what it's saying. So I'm going to let you formulate that out into the problem itself. You'll see that concept return. For what range of BOD5 would this dilution produce the desired results? So essentially, what range of wastewater strength are we talking about here? And I'll just write that as high mark and a low mark. Okay, so here's kind of the approach to take. For the high mark, that's going to be the highest amount of oxygen removed that we can do. Did a quick calculation for the dilution factor. The problem told us we had 10 milliliters of the sewage sample in a 300 milliliter total bottle. So that's 10 over 300 or 1 over 30 is our dilution factor. And so for the high mark, we said we can't go below 2. So we could have just written 2 here. That would be fine. 9 minus 7 is 2. But just to be clear at what that means, we started with 9 milligrams, we ended with 2, and so this is our DO initial and minus DO final, right? That was from the equation we just had there. So I meant 9 minus 7 there, sorry. Okay, so that means we are left with just 2 divided by 1 over 30. So essentially that's 2 times 30, which would be 60 milligrams per liter BOD. That might be the low mark. Is that the low mark? Yeah, that's the low mark, sorry. Got that backwards. You're free to hold that against me, but I've taught, this is my 3rd class today, so I'm going to forgive myself at least. Okay, so the next one would be 7. We do 7 times 30, and that gives us 210 milligrams per liter BOD. Okay, so that would be our range from 60 to 210 milligrams per liter, and typical range for wastewater is about 600 to 500 milligrams per liter BOD. That's just a general range for wastewater, broadly speaking. So that would certainly, a dilution of 1 in 30 would certainly catch most of the low range of wastewater strengths. And if you had a higher strength wastewater, you'd have to dilute more than that. So if you're doing a BOD test and you're not sure, which is likely, then you might try this dilution range and then perhaps another one that's further diluted. Maybe you try one that's not quite as dilute. If you were concerned it might be pretty weak and weaker than normal wastewater, or it's maybe treated wastewater. Okay, does that kind of make sense, that process there? Okay, so the whole BOD calculation on the front end in terms of here's the bottle, here's your measurement, what happened, is relatively simple. It gets a tiny bit more complicated, but it's still just kind of an algebraic analysis here. If you add the fact that you might have to add a seed to your water. And a seed, what I mean is some bacteria. So when you add some bacteria to your system, you're adding it so that you make sure that your water does have some biological activity in the first place. If you have a raw wastewater, you probably don't need to. But if you dilute it a whole bunch, maybe you actually should supplement it a little bit. So in this case, last time we said we had, it was filled mostly with diluted kind of pure water. But essentially what we're doing is we're adding a little bit of seed water in with that dilution water, and then the rest is wastewater. So, oops. The point being is we're adding 3 elements. We're adding dilution. We're adding dilution, we're adding the wastewater, and we're adding a little bit of this seed stuff. And that seed stuff, in order to keep a culture of bacteria happy, it's going to have some biodegradable organics in it. So we're actually adding a little bit of BOD when we do this seeded dilution. So it just complicates it a little bit. We have to account for then, if we're trying to find the BOD in our sample, or in the, that's the mixture. If we're trying to find the BOD in our sample here, that's probably the ultimate goal. So we'll just call that the target. We can measure the BOD in the mixture by this jar analysis, but we also need to know something about how much BOD we just added with the seeded dilution. And so typically what we'll do is we'll measure just the dilution water itself with the seed in it to see how much BOD is in that, and then separately we'll do the mixture with the wastewater or the other, maybe river sample water, whatever the sample is, and those two combined to check that. And then essentially the BOD of the mixture is the addition of the two, so when we do a series of 2 jars at the same time, we'll get both pieces of information. We'll measure this one directly, and we'll measure this one directly. So we'll measure that one separately, and we'll measure this one directly. And by doing so, we'll then be able to know, given the volume that we had of the wastewater, how much BOD was in it. And you see here also a mass balance on BOD, because we have some total BOD in the solution, volume of the mixture, that's the BOD of the mixture. That's going to be the addition of the BOD in the wastewater times the concentration, times the volume of that wastewater or otherwise sample, and the BOD of the dilution times that dilution volume. Okay, so it's the same process, just adding a little bit of algebra here with the mass balance in that manner. M meaning the mixture, D meaning the dilution, and here now we're saying that the P factor is the volume of the sample divided by the sample plus the dilution. It's essentially the same as it was. We're now calling it VD for dilution. Maybe we already did. One thing to keep in mind here is you can actually say 1 minus P is equal to, if we did 1 minus this will be equivalent to saying the volume of dilution divided by the volume of the mixture. Okay, it's just a bit of fraction analysis. That comes into the next slide, and we'll use that fact to derive, essentially we're simplifying for BOD of the wastewater. We're going to solve for that in terms of these other components. If we can solve for it in terms of BOD in the mixture, BOD in the dilution, and P, it becomes very convenient. So that's the only thing this slide is doing, is deriving those pieces so that we can have an equation to just straightforward solve for BOD in the wastewater or in whatever sample we're looking at. Don't really have time to go through that derivation. It's just a bit of algebra. It's just rearranging essentially from this guy, which is kind of a straightforward mass balance concept, getting down to this. So you'll have this equation. I wanted to talk about it even though I didn't really have time to cover it all the way, because you'll use this and we can solve problems with that. You will in the homework for finding the BOD in a diluted sample that has a seeded component. Okay, any questions or issues? All right, so that's all for today. We'll see you on Tuesday next week.